Good guess. I'm audible. So we have written here the momentum thickness up to this point. So note down further. Okay. So laminar flow over the flat plate. The laminar flow over the flat plate. So here, guys, few things are very important to note down. This is the fixed plate. The fluid is flowing over these fixed parallel plates, and there is a boundary layer formations. Note down. Blasius results. I'm audible, right? All of you? Note down the Blasius results. So Blasius results we call exact solution. He has proposed an exact solution for this velocity profile and displacement thickness and all, that is the boundary layer thickness. This results to be used when velocity profile is not given in the problem. Whenever velocity profile is not given in the problem, we have to use the Blasius results. Right. So what are all the Blasius results? First is boundary layer thickness. Note down 5 into x local Reynolds number. Let's say we are calculating the x from here to here. So what is my Reynolds number? Rho into u infinity into x by mu. That is what we are calling local Reynolds number. Rex will be local Reynolds number. That is the boundary layer thickness. Note down second displacement thickness, that is 0.664 into x divided by under root of local Reynolds number. Note down displacement thickness 1.72 into x local Reynolds number. Means do not write like this, otherwise you will confuse. So Rex. Fourth one will be shape factor, that is displacement thickness by momentum thickness. That is 2.59, because 1.72 divided by 0.664, you will be getting the shape factor. Note down the fifth term, local skin friction coefficient, 0.664 divided by under root of Rex. That is a local skin friction. If that is a local, then what is the average? If that is a local skin friction, then what is the average? Average will be CD. For throughout the length of the plate, on an average, what is my CD value? Coefficient of drag. That is, we have to calculate by using the integration, a very basic integration. Is it done for all of you? If you want to calculate the average skin friction coefficient, then what you have to do, 1 upon L, 0 to L, Cfx into dx. You have to perform the integration. Cfx means at a particular location. CD means on an average for throughout the length of the plate. Throughout the length of the plate, what is my CD value? Done? Note down CD value 1 upon L, 0 to L, Cfx into dx. That is 1.328 divided by REL. What is REL? The Reynolds number based on the total length. Make a note of it. Done? Now, note down the turbulent flow, turbulent flat plate boundary layer. Here, when the velocity profile is not given for the turbulent flow, one common approximation is there. That approximation of the turbulent flat plate boundary layer will be 1/7 power law. U by U infinity will be y by delta to the power 1 by 7. That is the approximate boundary velocity profile for the turbulent boundary layer. Based on this, we have some Blasius results. Again, we have the Blasius results for the turbulent flow also. That is what we will discuss. Note down. Note down the heading and directly you note down this formula profile. Done. This is one of the very important segment. See, for the laminar flow, we have discussed these all the Blasis results. All are Blasis results. Right now, look at very carefully. For the laminar flow, delta by x is written as 4.91. We can also write or 5 by Reynolds number. That is all. Both are correct. 4.91 and 5 both are correct. The good observation you will observe from here is that this turbulent flow, this particular values 1, 2, 3, 4, all these values are obtained from 1/7 power law. That means whenever in the problem they have mentioned 1/7 power law only, this turbulent flow relationship given for obtained from 1/7 power law combined with some empirical data, where in the problem they will be giving you empirical data, something along with the 1/7 power law, then only we have to use this classes results for the turbulent flow. Until unless they mention any empirical data, if they mention only 1/7 power law in the problem, we have to use this one. If they have given empirical data, we have to use this one. More accurate, this is more accurate, but this is based on some velocity profile. Rather to say, this is not the Blasis results, these are the von Karman results. This one approximates results, right? These are the exact results, but in exam they mention only 1/7 power law. That's it. They have given velocity profile as u by u infinity, y by delta, 1/7. That's it. No other data. That means we have to use this one. No empirical data means only we have to use this delta value, delta star, theta, cfx. Make a note of it and put an arrow. This we have to use. This particular column we have to use once they have given this thing, what we call 1/7 power law, 1/7 power law combined with some empirical data. Note down very quickly. Already we have noted down these results. 1, 2, 3, 4. Already we have noted down. Done? Is it done? Now try to solve this question. The laminar boundary layer over the flat plate held parallel to the free stream conditions. Uh, at a distance 0.2 meter, they have given delta 1 as 5 mm. At the downstream distance 0.8 meter, they are asking what is delta 2. So they have not given any velocity profile, so we can use Blassius results. What are the Blassius results? 5 into x divided by Reynolds number. 5 into x divided by what? Rho u average x by mu. So delta will be directly proportional to under root of x for a fixed rho u average value and mu value. So delta 2 by delta 1 will be under root of x2 by x1. B will be correct. Note down quickly. Done. Now, when you see this one question they asked recently this year only, very simple one. Consider a Blassius solution for an incompressible flat plate boundary layer, that is a laminar. The momentum thickness will vary according means with respect to distance x as what? That's one of the simple questions they have given. What is the theta formula with respect to Blassius? According to Blassius, what is the theta formula? 0.664 x divided by Reynolds number. Again, theta will vary under root of x for a fixed rho u average and viscosity. B will be correct. Make a note of it. Now, tell me the answer for this very quickly. That's a very simple, no velocity profile. We have to use the Blassius results, and the answer will be B. Ratio of displacement thickness to momentum thickness. They are asking safe factor. Try to solve this question. Here, velocity profile they have given as 3 by 2 y by delta whole cube. Now they have given the velocity profile, so we have to be very careful. The wall shear stress means at y equal to 0, du by dy at y equal to 0. 3 by 2 1 upon delta minus 1 upon 2 3 y square by delta cube. But y equal to 0, that will be gone. So we will be left with 3 by 2 times of delta. Mu is what? 1.85 10 power minus 5 into 3 divided by 2 delta. Now delta, don't use Blassius results. We have to use formula 1 minus u by u infinity into dy. Understanding my point? Into dy from 0 to delta. From 0 to, yeah, correct. So, but here delta they have given the 5 mm, right? So, I need to calculate. Now tell me the answer. 6 mm. All of you are getting 6 mm as answer. No, mm. How it is mm? No, no, no. Wall shear stress they are asking in 10 power minus 3, so it will be 54, right? 5.4. Now, what is the exact value? First of all, tell me the exact value. 1.10 power minus 5 into 3 divided by 10 into 1000. So I am getting 5.4 into 10 power minus 3. So 5.4 will be the answer. Done this one? This question done? Try to solve this question. The normalized theta by delta they are asking. So very simple. Theta will be what? Correct. Correct. U by u infinity, y by 1 minus u by infinity 0 to delta. See, y delta to infinity plus delta to infinity. Delta, see what they have given, delta to infinity, u by u infinity 1 minus u by u infinity into dy. They have given as 1. 1 minus 1, that is 0. That will be gone. Delta star, sorry, theta, you will be getting what? Y by delta into dy minus y square by delta square into dy. So you will be getting delta by 6. Theta by delta 1 upon 6. Now Note down von Karman, von Karman integral momentum equation. This will give you approximate solution. Glaciers will give exact solution, but this will give approximate solution. Tau divided by tau naught rho u infinity square is equal to what? D theta by dx. Tau naught will be mu into dy by dy at y equal to 0. It is valid for both laminar plus turbulent flow, but for flow over the flat plate only. We use this when velocity profile is given in the problem. Given in the particular problem. Note down some values that I am giving you right now. Linear velocity profile, parabolic velocity profile, cubic profile. U by u infinity, that is y by delta. U by u infinity, that is 2 into y by delta minus y by delta whole cube. Y by delta square, sorry. U by u infinity, that is 3 by 2 y by delta whole cube. First is boundary layer thickness, 3.464 into x divided by. Now this is very simple. You will get very easily. I will be showing you one calculation. I will send this in on the WhatsApp group. You know, this for linear velocity profile, so that you can get everything for parabolic and cubical. Momentum thickness, you can write delta by 6. Here you can write delta by x will be equal to 5.477. 4.464. Theta will be 2 delta by 15. Note on this table. One more is there, drag coefficient. Drag coefficient. Average drag coefficient. Yes. Now, is it done for all? Sorry. Here you can write in same way. You can write third one, that is for the laminar. Sorry, the linear velocity profile, parabola, cubical. CD, average value for the linear one will be 1 point divided by a Reynolds number based on the total length, 1.46, 1.293 divided by what you are observing, what the observation you are making. CD values keep on decreasing as the velocity profile become cubical from linear to cubical. That means like this. The flow is fully occupied as compared to the linear velocity profile. This was the complete area, right? It has to flow with this full velocity profile should be there. But as we are assuming the linear velocity profile, lot of flow is missing over here. A lot of momentum loss will be there. A lot of drag force will be there. A lot of CD value. Or is it something else? Tell me, guys. A very good observations. By looking at the values, what you are making the observations. See the value, CD value. 1.154. It is a very less as compared to parabola and cubical. But whatever the discussion I have made, is it not looking like a very contradictory statement? Tell me, guys. See, based on the CD value which I have given you just now, tell me what the observations you are making. Cubical velocity profile, I told you 3 by 2 y by delta minus y by 1 by 2 y by delta whole cube. The same cubical profile here, what we have written. Same this one. Tell me, guys. You just compare the values of theta, momentum thickness, in which case it is larger one. This is approximately 0.139 times of delta. It is 0.133 times delta. It is 0.167 times of delta. Tell me what you are observing, guys. Both cubical and parabolic is almost same, almost having the same value, and it is lesser value as compared to the linear velocity profile. Here huge momentum loss is happening. See that huge momentum loss is happening, right? Theta is what is the drag force? Drag force we have written rho u infinity square into theta. If theta is more, drag force will be more. So for the linear, drag force will be more. But here what you are observing, that CD value for the linear one it is lesser. What the conclusions you are making as compared to parabolic? In the linear one, the CD value is lesser. Tell me, guys. Any reason you are observing over here? See, that is a very that is a very wide discussion, because why it is a very wider discussion. See, delta is here, it is lesser. The boundary layer thickness for the linear one it is a lesser as compared to parabolic velocity profile. You observe very carefully. Delta is also different. So theta you can compare when you have same delta. When you have same delta for linear, parabolic, and this. So again, you can make the make comparison, but you have to keep delta to be very similar for all the velocity profile. So it is very difficult to compare, right? And it is very difficult to predict the CD value just based on the profile. Understanding what I'm saying? So whatever the actual reason is there, that whenever we have the less amount of flow to be occupied, Definitely CD and theta value will be more. There is no doubt about it. But why CD value is here, it is coming less? Because delta is also less as compared to other two profile. When you keep delta to be same, when you keep delta to be same, in that case, in that particular case, what will happen? CD will be coming out to be more for the linear velocity profile, right? Try understanding. Now, so this is a discussion about the CD value. I will send all the calculations for one profile, other you can calculate very easily how to proceed with the von equations. Now we have done with this boundary layer theory. One more thing is being left out over here. Just wait. I think... So I have given that when we have to use when the velocity profile is given in the problem. Okay. So note on the next chapter, dimensional analysis and similarities. And why we have to use this particular chapter? Any physical significance? Anybody know that? This dimensional analysis and similarities. Any physical significance of this chapter? Why we have to use it? Generally, in many cases in real life engineering, the equations, whenever you suppose I have given you the task to design for aircraft, for example, right? If I just make the rough diagram of that, sorry, this has to be symmetric. Whether it is a symmetric or asymmetric aircraft. And for example, we have this wings and all control surface. Now here, what I'm saying, symmetric, good. So it is symmetric about both the vertical plane or horizontal plane or what? Let's say this is a prototype and we want to do the analysis of this aeroplane. Like we have to calculate how much of drag force is there, how much of drag force is there, right? And how much of drag force is there, how much of yes, weight is, we can calculate how much of lift force which is being generated, how much of lift force which is being generated in that. So the good question is that if you want to design any aircraft, we have to calculate what is the pressure value, what is the drag force. A very new aircraft, let's say I want to design electric aircraft, right? A very new thing. There is no jet engine or maybe turbo, whatever the turbofan engine is not there, right? Definitely we will be running with the help of motor. Now that's a very new design. Everything will be new for the electric aircraft, right? As compared to the conventional aircraft. And that is the task will be given to you as an aerospace engineer. You don't have any data, you don't have any equations, you cannot use the same conventional model equation to this particular electric aircraft. So what you will do, instead of doing the experimental, making the actual aircraft will be very tedious and very costly. What you will do, you will do the dimensional analysis. What you will do, you will be collecting a lot of data first of all regarding that electric aircraft. And then what you will do, that you will try to stabilize that whether my drag force is, in that case in the electric aircraft, whether my drag force is directly proportional to u square or directly proportional to u to the power 1 or u to the power q. How actually, if I in a wind tunnel testing machine, if I just place my stationary electric aircraft and I'm flowing my fluid to flow over that, what will happen? If I increase my velocity, the drag force will increase, but whether it is increasing at a rapid rate or at a very very slow rate, that can be stabilized by knowing the dimensional analysis. In this one, what we are doing, we are just thinking that drag force, it is a function of what are all the parameters: rho, area, u infinity, area means diameter, or maybe some other geometry, right? Viscosity. All these parameters are there which is affecting this drag force calculations. When you try to see that, okay, we have developed some relationship between drag force and velocity, drag force and density, now you can change the fluid condition. You can vary the change. You can take different fluid density, you can take different fluid velocity, so that you can get to know exactly which parameter is affecting a lot this drag force, so that you can design very carefully accordingly. And after that, once you know that speed is definitely affecting my drag force, you will design your aircraft for very worst speed in a particular actual test operations, or whatever the experimental thing you will do. So before going for experimental setup, what you will do, you will do the dimensional analysis, so that it will reduce your cost and it will save the money also. Otherwise you have to keep multiple time different velocities to get the results of drag force, and that is a very tedious job. So definitely before going for any experimental setup or any experimental kind of thing on anything, we will first do the dimensional analysis and modeling. So make a note of it. Now, after doing the dimensional analysis on the basically model, which is a replica of prototype but of the smaller version, right? When you do the analysis, what are all the careful things you need to be uh, you need to take care of? Which are all the things that you need to take care of? Suppose I have basically taken the smaller version of a big aircraft like this, for example. Now if it is flying like this, for example, so this is my model and this is my actual prototype. So whatever analysis we will do for the model one, for example. Whether results of the model, whatever the results we will get, drag force and all, we can apply to actual one. And if you are able to apply, under which condition we can apply. Tell me guys. In many cases in the real life engineering, the equations are either not known or it is too difficult to solve. Oftentimes, experimentation is the only the method of obtaining the reliable information. In most of the experiments, to save the time and money, tests are performed on a geometrically scaled model rather than full scale prototype. In such a case, care must be taken to properly scale the results. So here we introduce the powerful technique called dimensional analysis, so that we can apply our results which we have done on which we obtained from the model to be applied to the prototype. So what are all the steps to be taken? Whenever you have a big engineering problem, any ship or maybe any aircraft you want to design, you will make this a smaller version of that, a scaled version of that. Again, before going for experimental thing, for that scaled version, you will do the dimensional analysis. You will get some constitutive relationship between the drag force and velocity, or some other parameter that is affecting a lot, that is affecting the most that particular drag force or any other parameter. If you get to know that this is a most affecting parameter, you will take care of that parameter very carefully. And after getting the results from the model, after getting the results from the dimension analysis, and after doing the experimental thing, whatever the results you got, that results whether you can apply to prototype or not, that is the second question. That you can apply when you have the similarities. Which are all the similarities you should have? You should have geometric similarity, you should have kinematic similarity, and third, you should have dynamic similarity. Until unless you have these three similarity to be there, you cannot apply the results of model to the prototype. So here, note down, primary purpose of dimensional analysis are to predict the trends in the relationship between the parameter, like how the drag force is varying with respect to velocity. I'm just giving for example, it can be anything. Second, to obtain the scaling laws so that the prototype performance can be predicted from the model performance. I will discuss what are all the scaling laws are there. Now, how to develop the relationship? The first question is how to develop functional relationship. How to develop some functional relationship? Again, that is a very simple. If suppose if I'll be taking one example, that example I can take anything. Uh, for the sake of simplicity, what I can take, let's take the example of let's say uh, the ball which is being hanged from this string. You know that string we have the tension. Definitely we will be having a tension. There will be some mass. That is the weight of the ball. And if I just swing it, so definitely it will make a what? Periodic motion, right? Simple harmonic motion we will be getting my point. And the length of the string will be, let's say, L. How this time period T, time period, let's say T dash, how the time period of this ball will be there, on which are all the parameters will be affecting most this time period. So let's say T dash will be the function of, here we have length as well as G. These are the two affecting parameters, that is the length of the string as well as the weight of the body, that is the G value. Now for example, I can write T dash will be equal to K times of L to the power A G to the power B. Now this is the time period. Time period, what is the unit of time period? Second, right? M0 L0 T. And what is the length unit? L to the power A. G is what? LT minus 2 to the power B. Now you try to equate the coefficient of M, L and T. What you will be getting? 0 is equal to what? A plus B. That is the coefficient of L. What is the coefficient of T? 1, that is minus 2B. So B will be what? Minus 1 by 2. A will be what? 1 upon 2. So what is the time period will be depending on? Time period will be depending on what? L to the power 1 by 2, G to the power minus 1 by 2. So T dash will be K times of under root L by G. So from the dimensional analysis, you got to know that the time period will depending on what? Length as well as G. The lesser the G value, time period will be more. That means same ball, if I place in moon, where the G is what? G of moon is what? G of earth divided by 6. It will oscillate with a high time period. Then what will happen? What will happen? G value is got increased or decreased? G value is getting decreased, but T dash value will be what? Will be more as compared to the earth surface. So at least before going for experimental thing, we got to know that, okay, these are the functional parameters will be affecting a lot this time period. But the next question will be how to get K value. K value you can obtain from the experimental thing. And by the experimental, we got to know K is what? 2 pi under root of L by G. And this is a very famous formula. Everyone know this one. Check it out. The time period of a ball which is being hanged, pendulum, perfect. So very first thing is that this is the depending variable, these are the independent variables, right? And how to develop some relationship with the help of what? With the help of dimension analysis and similarities. Once it is done, let me know. Is it done for all of you? I think you can note down afterwards as we have less time. Half an hour is there. Now, note down similarities. These are the most important thing. Whatever the model is there, that model results can be applied to prototype or not. That depends on three things. What is the geometric similarity? Whether geometric similarity has been exist between model and prototype or not. Kinematic similarity exists between model and prototype or not. Dynamic similarity has been exist between model and prototype or not. So those are the questions that need to be answered. Now, I'm not skipping anything, even though we have the time constraint, so that I know the importance of each and every topic that can be asked in GATE exam. And definitely, whenever you will not be, uh, you know, anything, if I just skip that one, you will also skip. And if that will be coming in GATE exam, you will definitely leave that. So I cannot take at all any amount of risk over here, right? Let it take any amount of time, but you please try to stick with that, what I'm saying to you. Principle of similarity, that is the geometric similarity. What is the meaning of that? Each and every dimension of prototype should be scaled down in the same ratio. What is the meaning of that? Let's say we have prototype of cubical element LB height. This is my prototype. Let's say you have a smaller version L1, B1, H1. This is your model. And my dear friend, for example, if you are reducing L to L1 in whatever the ratio, let's say initially it was 5 meter and you got reduced to 2 meter. That means this is 5 by 2. In the same ratio, you have to reduce B by B1, H by H1. You cannot take B1 value to be certain random value, let's say 10 mm. You cannot take. No. It has to be 5 by 2. Let's say this is nothing but 3 mm, 3 meter. Then it has to be 3 by B1. Then it has to be B1 will be equal to what? 6 by 5. That has to be 1.2 meter. You cannot take 2 meter or 1.4 meter. It has to be 1.2 meter. Then only we can say geometric similarity has been exist. The model must be the same. Model must be the same shape as the prototype, but may be scaled by the same constant scale factor. This is the constant scale factor. That has to be same for all the dimensions L, B, H. That is your geometric similarity. Kinematic similarity, again, it's a very simple thing. I'm explaining in the same figure. Look at very carefully. I'm taking point number one, point number two, point number one, point number two. For the kinematic similarity, the velocity and acceleration of the corresponding points of model and prototype should be in the same ratio. What is the meaning of that? See, the meaning is very simple. Whatever the velocity is there at point number one, let's say velocity of prototype 1 point, velocity at 2 point will be v2p. Now here what I'm writing, understand, v1p, whatever it may be, the velocity at point number one for the prototype should be velocity at point number one for the model. They should be in the same ratio for all the points. You cannot have the certain at the point number two, you cannot have the random velocity of model. It has to be in the same ratio as the previous point has. Whatever the ratio we got, it has to be in the same ratio. Right? That is what the kinematic similarity. Same we can apply to acceleration also. Same we can apply to acceleration also, my dear friend. Right? So make a note of it. Again, whatever the things we have discussed, geometry means dimensions, kinematic means velocity and acceleration. A very similar thing will be there for the dynamic similarity, that means forces. Forces of the corresponding points of the model and prototype should be in the same ratio. Both magnitude and direction. See, whatever the direction is there, it has to be same directions. You cannot have a certain random direction like this. Point number one, in the model, you cannot have like this. So a lot of precaution we need to be take care of. It's not very easy thing. A big aircraft is there, you reduce down or scale down to the particularly camera size or maybe a room size aircraft. uh, you might be thinking, sir, that's a very simple thing, I can make it of a very anything. But you have to maintain the similarities. Then only whatever the experiment you do on a scaled version can be applied. Whatever the results you will get can be applied to the actual prototype once you satisfy all the three similarities. So it is not a very easy thing, as you might be thinking, to do the any experiment. Now, dynamic similarity, again, a very easy concept. Here, whatever the point, let's say any force, I'm taking any force. Dynamic similarity is achieved when all the forces in the model flow is scaled by a constant factor to the corresponding forces in the prototype flow. Sir, I didn't get anything. Let me explain. That means any force. Any force means any force, like inertia force, pressure force, viscous force, any force, whatever you bring, weight force, right? The gravity forces or any forces. Whatever the forces, let's say inertia force of the model and inertia force corresponding same point at point number one for the prototype. Let's say this ratio for this particular force is there. It has to be same for the viscous force in the model, for the viscous force in the prototype. Whatever the forces you have, that forces ratio of corresponding model and prototype should be same. That ratio should be same. This ratio should be K, constant, that has to be same. That ratio should be a same, and same. That cannot change. That simply cannot change. Viscous force, or you can write gravity force of the model, gravity force of the prototype. You cannot have a certain, a very random viscous force in the model. It has to be calculated from this ratio only. Let's say you have decided my, let's say this is my, for example, prototype, and this is my model. For example, let's say we have the forces here, inertia force like this, and we have the forces here, inertia force like this, and I know the two values. By the two values I will be getting one ratio. Let's say inertia force for the model, inertia force for the prototype. We got this value as K. All the forces, gravity force, surface tension force, elastic force, whatever the forces will be there, it has to be in the same ratio as given by this K. That's it. So now when you just compare these two things, then what we can write? Inertia force of the model to the inertia force of the, sorry, viscous force of the model will be equal to inertia force of the prototype to the viscous force of the prototype. Reynolds number of the model, that is equal to Reynolds number of prototype. This is called Reynolds law. Make a note of it. Reynolds model law. Even pressure force of the model should be equal to pressure force of prototype. Should be in the same ratio. Dynamic similarity is achieved when all the forces in the model flow is scaled by a constant scale factor to the corresponding forces in the prototype flow. The ratio of the forces, different forces, to the corresponding points of model and prototype should be same. That's it. That's a very simple and very straightforward definition of dynamic similarities. Now done. Can I move to the next one? To have a complete similarity, note down. To have a complete similarity, that means whatever the results we are getting from the model, if we want to apply to prototype, geometric similarity, kinematic similarity, and dynamic similarity should be same. Geometric, kinematic, and dynamic similarity should be same. What will happen if I maintain only dynamic similarity? Will it be okay? If I just maintain the dynamic similarity, will it be fine? Forces, rho L square V square. In that, length is also coming, V is also coming. So if I'm maintaining the dynamic similarity, automatically I'm maintaining geometric similarity, as well as I'm maintaining the kinematic similarity. So if you are maintaining only dynamic similarity, automatically kinematic and geometric similarity will exist. If you are only maintaining the geometric similarity, it will not guarantee you that kinematic and dynamic similarity will exist. If you are maintaining only geometric and kinematic, again it will not guarantee you that dynamic similarity will exist. Now we will see some of the questions that is a very important. Is it done for all? Now try to solve this question. A football meant to be thrown at 100 km per hour in a sea level air is to be tested using the 1/4 scale model in a wind tunnel. That means there is a model, there is a prototype. Two things are there for us. Sorry, two things are there for us. Model is there and prototype is there. Model which is being tested in a wind tunnel. So rho of model is what, 1000. Mu of model is what, 10 power minus 3. This chapter is very important. Every year, see 17, 20, 22, 23. Every year they are asking the questions. What is the rho of P? 1.22. Mu of P 1.78. Whatever the unit is there that you can write. That this year also it came. Now, what they have mentioned, that scale model, that means diameter of model to diameter of prototype is 1/4. Whatever the football is there, right? Whatever the diameter is there for a model and prototype is 1/4. The ratio of the model force to the prototype force will be what? Now, model force to the prototype force, I can assume any force. I can assume the inertia force. I can assume to be viscous force. Anything I can assume. That is up to me, because I know that the ratio of forces of corresponding points should be same. So either you calculate inertia force or viscous force, it's up to you. Now I am calculating inertia force. As a homework you can do for the viscous force. Inertia force, rho m lm square vm square, rho p lp square vp square. Now here see how we are getting, I already discussed. Inertia force is what? Rho l square v square. Fortunately here length lc is what? Characteristic length will be diameter. So what we can write? Rho m by rho p dm by dp vm by vp. But the good question is coming over here is that we know only vp, that is 100 km per hour. We don't know vm. How to calculate vm? That can be calculated by equating Reynolds number for model to the Reynolds number of prototype. This will always be valid as long as you have inertia force and the viscous force. Those two are dominating forces. So rho m dm vm by mu m, rho p dp vp divided by mu p. So when you do that, everything is given to you. Every data is given to you. You can calculate vm. That is coming as to be so here 27.416 kilometer per hour. Now, when you put rho m by rho p, that is 1000, 1.22, dm by dp, 1 upon 4 whole square. Vm by vp, what is the Vm? Vm, where is the Vm? 27.416 divided by Vp. Vp will be 100 whole square. So when you do this ratio, you will be getting 4. Means you will get 3.85, but they have given round up to nearest integer. So it will be 4. Done? The moment it is done, let me know. Or you can just note down afterwards. You just see only the procedure, how to solve it. Viscous forces also you can get. Viscous force is what? Mu V L C, mu V D. You can take the ratio of mu V D. Through that also you can get the answer. Same answer, 4. A similar problem you can solve as a homework. That's a very easy thing. Only you have to do Reynolds number of model, Reynolds number of prototype. Again, they have given the cylinder. For a cylinder, whatever the flow is there, so you can take the characteristic dimension to be what? A D. I told you, right? Characteristic length will be D only. In case of cylinder, length is not that important. This is a good question. Try to see. Here they have given they are asking the drag force on the sphere. But to calculation of a drag force, a very big thing is required over is that CD value. Right? So what you can just have the calculations. See, CD of model has to be CD of prototype. Why? CD we know that 1.328 under root of Reynolds to the power 1 by 2. If Reynolds number of model and prototype is same, then CD will also be same. So whatever the CD they have given in the problem, right? 0.5, it has to be same for both. It has to be same for both. That is for the model as well as prototype. And I don't think that any difficulty might be there after this discussion, because they are asking drag force on a model, that is half of CD of model, rho of model, u infinity m square and dm square. Means area, whatever the area is there. So what they have given, or we can just equate CD of model, that is CD of prototype. So we can get f of model divided by rho m um dm square fp rho p up square dp square, and whatever they are asking you can able to calculate. Getting my point, all of you? All of you are understanding? Yes or no, guys? So Reynolds number of model and prototype has to be same. Once again here also, and see this particular value you can calculate, already given 0.5. See 0.5. So only you need rho m, that is also given, that is also given, and diameter of model, that is also given. Check it out. So you can very easily calculate. Right? Now this particular question, a very similar problem they have asked in 2017. A very similar. A cylindrical object is moving. Basically, what VP is given as 60. Half scale model, that means diameter of model, diameter of prototype is what? 1 by 2. The coefficient of dynamic viscosity of air and water. See, air means what? Prototype. So whatever the viscosity is given, rho p is what? 1.2. Now it has been tested in a water. That means water is what? Model. So rho m will be what? 1000. And viscosity of model is given, viscosity of P is given. Everything is given to you. What you have to do, you have to calculate the drag force on the model is given like this. They are asking drag force on prototype. It's again very simple. From the Reynolds number of model to the Reynolds number of prototype, you can calculate what you can calculate. You can calculate Vm. Once you know Vm, the drag force in the model to drag force in the prototype. That means any force I can take. I can take inertia force or viscous force. Let me take inertia force. Rho m lm rho l square v square rho p vp square dp square. You know this value 2280. You know Vm from here. dp you know, vp you know, rho p you know, rho m you know, vm you know. You can calculate fp. Again a very simple one. You will be getting the answer approximately 644. Nearest value you will get 644. Make a note of it. Now just note down very quickly. Done. Now try to see this question. One of the good question. The operating characteristic of a pump is given as Cp A into phi square, and Cp is given as P by rho omega cube d power phi, where phi is the flow coefficient and A is constant. D is the length scale, omega is the rotation rate, rho is the fluid density, P is about power required. Now they have given the flow coefficient phi is a function of what? Is a function of omega and d. Omega to the power A, d to the power b. So can we write phi is equal to what? K times of omega to the power A, d to the power b. Further, my friend, what we can do, we have flow coefficient. Flow coefficient is a dimensionless term. So m0, l0, t0, that must be omega. Omega is what? Rotation rate. Rotation rate means what? Rotation per second means what? 1 upon t. T to the power minus 1 to the power what? A. Diameter, L to the power what? B. Now equate the coefficient. What you will be getting, my friend? A will be equal to what? Minus 1. B will be equal to what? No, sorry. Just wait. Here it's a function of omega to the power A, d to the power b. So here what we can get? If we just equate the coefficients, no, it will depend on what? Rho also. What we can have it? Because if we write here coefficient, that will be 0, right? How it is possible? Here we have to write rho also, right? Because here it is, we have the flow density. Here whatever the flow density is there, that will also be the whatever the flow coefficient is there is a dimensionless flow rate, right? So it will depend on density also, rho to the power c. So here what is the density unit? Kilogram per meter cube. So what we can write? ml minus 3. So here we can write further ml minus 3. They have not given the relation, we have to derive it. So now you just equate the coefficient of mlt, what you will be getting when you just equate m, that is c, that is c will be what? 0 minus 3c plus b, that is equal to what? No, just wait. Here we can write discharge, right? It is the basically the function of discharge. No, 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 no. The, if all 0, then it is depending on certain things, right? See, we have to write q by dq into n. That is my flow coefficient, something like this. So it is depending on what? Discharge and as well as what? D, right? So what we can write? Phi will be the function of what? Q to the power a, because it is a dimensionless flow rate. So it will depending on the flow rate also. Then we will require omega to the power b and what? D to the power c. That one more thing I want to give. So to avoid this confusion, what the confusion I have, to avoid that confusion, you always write one shortcut. Whenever you are writing any set of repeating variable in the bracket, we call set of repeating variable. The set of repeating variable must be like this: geometric variables, kinematic variables to the power a to the power b, and dynamic variable. Three terms must be there. So you can have accordingly, you can adjust the power, like you can just place it d to the power a. Omega, that is a kinematic per second. Q will be dynamic term, that is meter cube per second. So that is by c, q to the power c. So now what you can have, m0, l0, t0. Q is what? Meter cube per second. So what it will be having the value? lq t to the power minus 1 to the power what? C. Omega is what? T to the power minus 1 to the power b, L to the power what? A. Now when you just equate the coefficient 3c, just equate the L coefficient first. A equal to 0. Oh, sorry. Again we are doing mistake. One depending variable we are deriving based on the independent variables. Then depending variables should be what? What should be the depending variables here? If you want to get the dimensionless term, we are already taking the dimensionless term in the left side. That is a blunder we are doing, right? We cannot do like this. So we have to take q. That flow rate will be depending on what? That flow rate will be depending on what? D to the power a and what? Tell me guys. Omega to the power b. Then what we can write? Q, that is k times of what? D to the power a omega times of b. Q is what? Meters cube per second. So L cube into what? M0 L cube T to the power minus 1. That is equal to what? L to the power A T to the power what? B. So what is the A value? A value will be 3. And what is B value? B value will be 1. Check it out. Getting my point? So here what you can write? Q will be equal to D to the power 3 omega to the power 1. So what you can write? Q by D cube into omega. That is my constant. That is my phi. Make a note of it. So with the help of dimensional analysis, we should be getting dimensionless term. Indirectly, we are putting the dimensionless term first. That is a blunder. They have given the hint also. Flow coefficient is a dimensionless. Volume flow rate is scaled with omega and D. Volume flow rate is scaled with omega and D. So we have to denote it like this. That's a very good question they have framed. Right? Because if you just calculate meter cube per second, here it also meter cube per second. So it will cancel out. We will be getting what? Dimensionless term. Now we get the relationship between Cp and phi. We got everything. And they have given that now omega, if the rotation rate is increased to the what? Omega, to 1.25 times of omega, and they have given the power which is being changes to 1 alpha times of P. They are asking what is the alpha value. So that you can relate very easily. How you can relate it? Cp they have given A times of phi square. Right? Cp data they have given A times of phi square. What you can put? Cp, you know that P by rho omega cube d power 5 A times of phi square. What is the phi? D q by d cube into n or omega square. So how to get the relationship? How to get the relationship between P as well as omega? Because only two things are changing here. So we can get P is equal to what? A times of Q square omega cube omega square rho. Sorry, rho will be here, and d cube into d power 5. So power will be directly proportional to what? Power will be directly proportional to what? What they have given? Power is directly proportional to what? Can we write power is directly proportional to omega from here? Check it out. So if you want to calculate P2 by P1, that is omega 2 by omega 1. When it is being changes, so it will also be what? Something like this. So P2 is what? Alpha times of P, where alpha is what? 1.25. Now some of you might be thinking, sir, is that this question is belonging to model and prototype? Yes. But here in this case, we are not changing the diameter of pump. Whatever the actual pump is there, that same pump diameter we are taking. Because see, no data has been given in the problem. Check it out. Anything they have given regarding this diameter changes, nothing they have given in the problem. Only they have given the rotation rate, that is the n value or omega value has been changed. Right? So we cannot take anything, we cannot make any comment based on D. Otherwise, we could have this pressure is what? Directly proportional to omega into D square. But diameter they have not given, whether it has been changed or not, nothing they have mentioned. So we will take diameter of model, that is equal to diameter of prototype, or D1 equal to D2. Here we denote it by 1 and 2, right? So omega 1 is what? Omega. Understanding what I'm saying? Tell me guys. So based on this relation, we have to vary our conditions. Yes or no? Done with this? All of you noted down? Yes, very quickly. Now the last topic, it will take not more than 10 minutes. That is a linear momentum equation that I will discuss. Just wait for 1 minute. Note down the next concept, the last concept, the linear momentum equations. The linear momentum equations. Whenever any fluid is flowing, right? Whenever fluid is flowing in a pipe, and let's say the pipe is there, when the fluid is flowing in a pipe, definitely fluid will exert some forces, opposite and equal forces. Opposite and equal forces will be exerted by the pipe wall onto the fluid element, and that is what we have to discuss. Let's say the fluid is flowing like this, and initially it is being flowing at a speed of v1 with the pressure which is being acting on this control volume p1. Here the pressure is acting p2, and velocity with which it is being getting out is what v2 we have, and this is what the control volume we have. The forces in the x direction will be what? The rate of change of momentum in x direction, that is the final momentum minus initial momentum. But initial momentum, final momentum, you have to note down very carefully. Whenever you are finding the forces by the wall onto the fluid element, the forces by the wall onto the fluid element, the forces by the wall onto the fluid element, whenever you want to write the forces on the fluid element by the wall, you have to write final minus initial. Whenever you are finding the force by water onto the wall, initial minus final. Right? Now here the good question will be that why this term is coming. That is a pressure force term. That is a pressure force term. Here this will be P2 cos theta, P2A2 cos theta. Here it will be what? P1A1. So what we can write, my dear friend? Fx plus P1A1 minus P2A2 cos theta, that is rate of change of momentum. Final momentum is what? Mass flow rate. Final momentum in x direction, V2 cos theta. Initial momentum is what? V1. Similarly, we can apply this equation Fy. If this particular pipe is in the vertical plane, then mg will also be coming into the picture. Mg will also be coming into the picture because we are assuming this force Fx and Fy like this. That is my positive quantity. If at all weight is acting in the downward, that has to be negative. But Fy minus mg, that is equal to final momentum minus initial momentum. But mg will be taken to the right side, that will become plus. But if the pipe is in the vertical plane, then only this equation is valid. Otherwise, mg will be 0 in a horizontal pipe. Sorry, note down the equation very quickly. Note down one more thing, P1 and P2 are the gauge pressure, not the total pressure. Not the total pressure. Do not add PATM. So P1 is given at say 5 kilopascal, P2 is given as 2 kilopascal. So and PATM is given 100 kilopascal. Do not say P1 equal to 5 plus 100. That is wrong. Only write gauge pressure 5 and 2. because atmospheric pressure not only acting here, it will be acting here also, it will be acting here also, it will be acting here also. Together, PATM will cancel out, and you will be left with only gauge pressure P1 and P2. Now, I think done. Is it done? Now, try to solve this question. A water is being accelerated by the nozzle at a speed of uh, 20 meter per second, and it strikes the stationary vertical plate with the mass flow rate 10 kilogram per second with a normal velocity 20 meter per second. And after striking the plate, the water stream splatters off in all the direction in the plane of the plate. Determine the forces needed to prevent the plate to move horizontally due to the water stream. That means we need to calculate force of the plate. Final momentum, initial momentum. Final momentum, everyone know that. What is the final momentum? Zero. Mass flow rate. What is the final velocity? Initial velocity in x direction. Final velocity, the moment it is striking. What is the final velocity? Zero. It is strike the plate, it is moving like this. That is of no use. We are writing the momentum equation in x directions. That is 0 minus 20. Mass flow rate 10 into 20 minus 200 Newton. The negative sign means what? We have assumed by using this particular formula, we have assumed by force of the plate that it is acting like this. That means it is a positive. But if it is coming out to be negative, that means the force exerted by the plate in these directions. Negative sign is coming is what? Our assumed direction is incorrect. We can also write force by the plate will be 200 Newton like this. Done? Now, this last problem we will solve. The large water tank is being fixed on a cart with the wheels and vane as shown in the figure. The cart is tied to the fixed support and a thin horizontal rope. There is a hole of diameter 5 centimeter on the side of the tank through which a jet of velocity with which it is coming and is striking. Whenever you are solving this type of problem in a linear momentum case, you try to make a control volume. I'm assuming this is my control volume. In this control volume, if I make this type of control volume, there's a no inlet velocity. There is no inlet velocity, nothing is there. Only outlet velocity is there. Then what we can write? Tension in the string will be what? The tension in the string will be what, my dear friend? If you just make this control volume like this, there will be tension T in the rope like this. And there is a velocity with which it is coming. So the net force we can apply, tension will be final momentum minus initial momentum. There is no initial momentum, nothing is entering, right? So T will be what? Final momentum, mass flow rate into velocity in x direction. So what is that? 10 cos 60. What is the mass flow rate? What is the mass flow rate? What is the mass flow rate with which it is being impinging out? The mass flow rate, how to calculate that? Rho into area into velocity with which it is coming out. So rho is what? 1000. Area is what? Pi by 4 d square, that is 0.05 whole square. Velocity with which it is coming out, that is 10. So when you just calculate what you will be getting, that is 1000 5 by 4 0.05 whole square into 10 into 10 by 2. So when you calculate, you will be getting what? 98.174 Newton. Check it out. 98.174 Newton. But if you just assume some different control volume here, let's say you have taken this control volume, and if you just apply the equation, very difficult for us to solve because we don't know P1 value. We don't know P1 because in the tension formula, we should be writing P1A1 also, right? That is final momentum minus initial momentum. Because here that is atmospheric pressure, so that is taken as 0, that is P2. But here we have the P1, that P1 we don't know because height we don't know. Rho GH, we don't know height. So selecting the control volume is a very important task in applying the linear momentum equations, right? So once it is done, we can leave for the day, and the remaining problem you please try to solve. Meanwhile, what I will do, I will be start sending the solution in the WhatsApp group for all the problems, which is there in the slides, as well as we will be having the discussion on different concept of what fluid mechanics. Varieties of question I will be keep on sending. Take those questions very seriously, guys. Whatever the question I will be sending in the WhatsApp from tomorrow onwards regarding fluid mechanics, you try to make a note of it. Boundary layer, laminar flow, fluid kinematics, circulations, each and every topic, right? Regarding each and every topic, I will be sending the question. You please try to solve those questions. If not, I will be sending the solution also, a detailed solutions. That will be a very new pattern question will be there, so that you will be habituated of seeing the concept and related questions, right? So be active in the WhatsApp group. Now, thank you all. Yes, yes. Whatever the small portion which is being left out, that will be covered by either aerodynamics faculty, or maybe I will be taking the fluid machinery. There I will cover, right? Hardly one or two topic is being left out. That I will cover through question also. Question series, whatever the series I will start in WhatsApp group. Through that, you try to see that question. And if concept is not being covered related to that topic, I will be sending the concept also before sending the solutions, right? Because I left this circulation and all because that will be covered by aerodynamics faculty.